So in this video we're going to look at another really important theorem about continuous functions in real analysis, and this is called the extreme value theorem, and this sits kind of side by side with the intermediate value theorem. They're both absolutely crucial and very intuitive theorems about functions that are continuous over an entire interval of the real line. So we're going to have a function then that we'll call f, and it's going to be defined on the closed interval from a to b, and it's a real value function, and it's going to be continuous everywhere on the interval ab. So for all p is an element of the interval ab, it will be continuous at that p. So the extreme value theorem says that if you have such a function, then it's going to be bounded, i.e. the values that the function takes over the interval is bounded above and bounded below. It cannot get indefinitely big and it cannot get indefinitely small. And it has a second part to it as well. It says that the function is going to obtain its maximum value and it's going to obtain its minimum value. So we can write this as follows. There's going to exist 2 points inside this interval. One point is going to be where the function obtains its minimum, and one point is going to be where the function obtains its maximum. We'll call the point where it obtains its minimum c, and we'll call the point where it obtains its maximum d. So there's going to exist a c and a d within this interval such that all the values of the function f of x here for all x within the interval are bounded by these two things, f of c and f of d. So they're bounded below by f of c. They're all greater than or equal to f of c. And of course, it's going to be equal at, for example, c, which is a point within the interval. And it's bounded above by f of d. So again, it's going to be less than or equal to f of d, and it will have equality when x is equal to d. Now, of course, there could be some other point that has this same value, f of d, but d is one of the points where it obtains that maximum value that it takes over the entire interval. So this theorem makes great intuitive sense, and to show you how, I've drawn a picture here. So we've got our interval ab here, and here's the value of the function at a, here's the value of the function at b, and we know, of course, that it being continuous everywhere on this interval ab means that when we draw the function, we can draw it as a continuous line. So we can start at this point and go to this point, and the line that we draw is going to be continuous. We're never going to have to take the pen off the piece of paper and move it. We can move our pen continuously along the surface of the paper to draw the curve that graphically represents our function. So it's intuitively clear then, by the fact that we can do that this function is never going to become either negative infinity or positive infinity. It's never going to go off to the infinite, because how on earth are we going to be able to draw a line from here to here nice and continuously if at some point the function has to go off, for instance, to positive infinity up here? That's not going to ever work intuitively. So it's intuitively clear then that the value of the function is going to be bounded. Let's now think about the second part, that it is actually going to obtain its maximum and minimum values. So again, this is quite clear from the fact that we can draw it in this continuous manner. So if we can draw it like this, well, at some point this continuous curve must reach its highest bit. There must be some bit that is the highest part of this curve, and there must be some bit that is the lowest part of this curve. And at that highest bit and the lowest bit, there will be a corresponding point in the domain corresponding to that bit of the curve, and those will then be the values in the domain that are being mapped onto the minimum and the maximum. So in the case of this picture, here is the highest peak of this curve, the highest value. If you go to any higher bit, if you draw any higher line, the curve isn't crossing that line. So this is the highest line which it crosses. And there must be some corresponding value in the domain here that is being mapped onto that value in the codomain for you to have plotted that point in your curve here. And equivalently, down here, in the case of the picture, this is actually the minimum height of the curve, and it actually corresponds to the a lower boundary of the interval. So in this case, c is going to be equal to a, and d is going to be this point here. So that's the intuition behind why this is going to be true. What we now want to prove is that it's true from our abstract analytical definition of what it means to be continuous at every point in the interval AB. So we'll start by proving that it's bounded, and the way we're going to do this is by contradiction. So we will assume that it's not bounded, and we will find a point in our domain where the function is then not continuous, therefore contradicting the initial assumption, and therefore it can't be the case that the function is unbounded. So really, to do this proof, we need to do two separate cases. We need to do the case where you assume that it's not bounded above and you derive a contradiction, and then we need to do the case where you assume that it's not bounded below and again derive a contradiction. That would then prove that it can't be either unbounded above or unbounded below, therefore it must be bounded above and bounded below, overall bounded. However, these two cases, the proof is virtually identical. It's the exact same strategy, so we're only going to do one of them, and then you'll know how to do the other one automatically from seeing the proof of one of them. So we're going to do the case of it not being bounded above and show a contradiction. So we'll assume, therefore, that our function is not bounded above, so it's unbounded above. So this is a beautiful strategy that we're now going to use to derive a contradiction. So we're going to construct a sequence, a domain sequence, that's going to then have a corresponding image sequence. And this image sequence is then going to go off and converge to infinity. And that's going to allow us to then conclude that there's a problem with continuity. And I'll show you how later. So this is how we're going to construct this domain sequence. So we'll start with the first term of the sequence, which is going to be x1, which is going to be somewhere in our domain, this interval from a to b. And I'm going to select this point by this criteria. So I'm taking this number 1, the term that you are in the sequence, and I want to find a point in the domain, an x1, such that it's being mapped onto something that is greater than 1. And I am assured to be able to do that because the function is unbounded above. So that means any number that you take, any positive real number, there must be a value of the function bigger than that. So there must be some point in the domain that's mapped onto something bigger than that. If that wasn't the case, then it wouldn't be unbounded above. It would be bounded above, because that real number would then be an upper bound. It would be bigger than all the other values of the function. So I can find such a point. I'm guaranteed to be able to find such a point by this initial assumption. Now, of course, this initial assumption is garbage, but from this is what I can conclude. So I found that first point. Now I'm going to choose the second term of my sequence. And the way I'm going to do this, you'll quickly see the pattern, is that I'm going to ask for a point in the domain such that the thing it's being mapped onto, f of x2, is going to be greater than 2. So because it's the second term of the sequence, I'm now making this number 2 here. And again, I can do that because it's unbounded above. So there must be some point in the domain that is mapped onto something that is greater than 2. Otherwise, 2 would be an upper bound. Now, it might have been the case that this number that you use in these two terms here of your sequence, it might be the same thing. You might pick the same point of the domain. For instance, this thing that you chose as x1, what if it's being mapped onto 4 by this function? Then it would satisfy both of these criteria, so you could have used it in both positions. That's okay, because we're going to continue this sequence on forever and ever and ever, and this pattern is going to continue. So at some point you are going to have to progress your sequence onwards, because whatever value your point is being mapped onto, at some point you're going to go beyond that. So I'll show you how. So we continue on in this same pattern. I want the third term to be picked such that f of this term is going to be greater than 3, and I'm guaranteed to be able to find such a point in the domain because it's unbounded above. And then you continue on creating more and more terms in this sequence, and in general the nth term is going to be such that f of that term is greater than n. So it's clear that this image sequence is going to tend to infinity, and that's because of the way that I've picked the terms in this domain sequence such that the corresponding terms in the image sequence obey these inequalities. So you can see that the terms of this image sequence are going to get and indeed stay indefinitely big, because if you go, for instance, up to this nth term here, this term and indeed all of the terms beyond it are going to be bigger than n, because if you look at the term after it, it's going to be bigger than n plus 1, the term after that is going to be bigger than n plus 2, and those things that they're bigger than are certainly bigger than n, so it and all the terms beyond it are going to be bigger than n. So indeed, the terms of this sequence are going to get and stay indefinitely big, so it's tending to infinity. Now, we could use this to contradict continuity if it was the case that our domain sequence was converging to some point in the domain. Because if this converged to some point in the domain, then by the fact that it's continuous everywhere, at that point that it's converging to, let's call it p, the limit as x approaches p of the function f of x must equal f of p, So that means that if you take a domain sequence that's converging to P, it must be the case that the image sequence converges to the limit, and therefore would have to converge to f of P, which it can't do because it's tending to infinity. So I'm going to sidetrack for a little bit to explain a small technicality, and these pictures here relate to this small technicality that is going to be helpful when we proceed with this proof. So in earlier videos in this playlist on real analysis, when we were talking about the limits of functions and the sequence characterization of the limit of functions, we were doing it in full generality. So we were thinking about this sort of case here. So here is a function, and if you consider the limit as x approaches p of this function, the value of the limit is where the hole is here. It's this L value. But in general, the value of the function might not be the same as that L value, so it might be something down here. Now, in this case, when we talked about the sequence characterization for the limit of this function, we said take any domain sequence that converges to P, but we had this requirement that the terms of that domain sequence could not actually equal P itself. And if your sequence in the domain fulfilled this requirement, then you could conclude from the fact that the limit as x approaches P of f of x is equal to L, that the corresponding image sequence will converge to L. Now, the reason you needed this requirement that none of the terms of the sequence were equal to P is because if they were equal to P, then their corresponding terms in the image sequence would be this value down here, which has nothing to do with the limit. You know, you could have the sequence P, 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 P forever. That is a sequence that would converge to P, but its image sequence would be f of P, f of P, f of P, f of P, which certainly doesn't converge to L. So you had to remove this point P in general for the sequence characterization of the limit of a function. In the case of continuous functions, you can relax it, you can get rid of it. This is now the picture corresponding to a continuous function, where the limit as x approaches P of the function is the value of the function itself. And in this case, you can take any sequence that converges to P, and you don't need this requirement. We can put a cross through this, get rid of it. The sequence can contain P's in it. It could indeed even be the sequence P, 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 and you can still conclude that the image sequence will converge to the limit of the function, which in this case is f of P. So if, for instance, we take the sequence P, 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 that now is allowed, its image sequence will be f of P, f of P, f of P, f of P, and of course that does converge to the limit because the limit is f of P, and a sequence of constant f of P's converges to f of P. So in the case where the function is continuous at P and the value of the limit as x approaches P of the function is equal to the value of the function at P, we can get rid of this requirement. We can conclude that if you have any domain sequence that converges to P, it can contain terms that are P, it could not contain terms of P, it doesn't matter. You can immediately conclude that the image sequence will converge to the limit, which is f of P. So I hope you're happy with that explanation. You can turn this explanation extremely easily into a formal proof. I'm not going to do that. I hope that you've got enough intuition from previous videos in the playlist about the epsilon definition for the convergence of a sequence and the epsilon delta definition for the limit of a function that you're able to do that for yourself. So instead I'm going to use the famous line that maths lecturers use, which is, the rest is trivial. So back to our main proof then. So if we could prove that this domain sequence converges to some value P in the domain, then we would have a contradiction because by continuity at the point P, it would have to be the case that this image sequence converges to f of P, which it doesn't because it's tending to infinity. However, can we conclude that this domain sequence converges to a point P? Well, the answer is no, you can't. But an incredible theorem that we already know from real analysis is going to save us here, and that's going to be the Bolzano-Weierstrass theorem. So the Bolzano-Weierstrass theorem tells us that any bounded sequence has a convergent subsequence. This sequence that we have constructed here in our domain is a bounded sequence because our domain was bounded. It was the interval AB. So all of these terms in this sequence were somewhere inside this interval AB. So it was bounded above by B and bounded below by A. Therefore, you can apply the Bolzano-Weierstrass theorem. There must be a subsequence of this sequence that does converge to some value in this domain. So I've drawn this out here. I've drawn my sequence again out here, but I've put much more terms here to illustrate what we're going to do here. So I've got all the way from x1, x2, x3, x4, all the way up to x11, x12, and of course it goes on for a very, very long time. Don't make me draw all of them. But what I can now conclude is that there is some subsequence of this sequence that is going to converge to a value that we'll call p in the domain. So just for the sake of showing pictorially what's happening here, let's say that this is our perfect subsequence. So these terms in blue are the lucky terms that are being chosen for the subsequence. And remember, the way you construct a subsequence is you just go along each of these terms and you decide, is it going to be included in the subsequence or not? So x1 has gone to the bin, it wasn't included. x2 was lucky, it survived. x3 went to the bin, x4 went to the bin, x5 survives, etc. And then this is the new sequence that we're constructing here. So it has to be in the same order. So the terms that survive have to remain in order. So you have x2, x5, x8, x11, x9, x11, and so on. So this is going to be convergent, and it will call the value that it converges to p. Now let's think about what the image sequence of our convergent subsequence is going to be, and this is the reason I drew this out so long, so that I could also draw out its image sequence so long and show you pictorially how the image sequence of our subsequence is going to be a subsequence of our image sequence. So here is our entire image sequence moved down here, f of x1, f of x2, f of x3, etc. They take up more space, so I haven't actually managed to draw it all the way up to f of x12 like the domain sequence was drawn, but you get the idea. And then if we take the image sequence of this convergent subsequence, you can see we're just going to pick the corresponding terms in the image sequence here and put them into a subsequence, and that subsequence will be the image sequence for our subsequence. So we picked x2, so we need to pick f of x2 here. We picked x5, we're going to pick f of x5 here, etc. 8, 8, 9, 9, and then 11, 11, etc. So this subsequence here, which is a subsequence of the image sequence, this is going to be the image sequence of this subsequence. So x2, f of x2, x5, f of x5, x8, f of x8, etc. So we know that the original image sequence tended to infinity. It got and stayed indefinitely big. This subsequence of the image sequence is also going to tend to infinity, and the reason that you can see that is it's going to have to get and stay indefinitely big as well. So if you pick any positive real number, we know in the original image sequence that there is a term such that for that term and all terms beyond it in the tail end of the sequence, they are bigger than that number. Now, at some point in your subsequence, you are going to get to a point where the terms beyond that are all picked out of this tail end of this sequence, because there's only finitely many terms before it. So at some point you're going to get past those finitely many terms, and then you're going to be into this part of the sequence to create your subsequence from. So from that part of the subsequence onwards, you can be sure that all the terms in it are going to be bigger than that positive real number, because we knew it for the original sequence. So yeah, you can conclude that any positive real number, there will be a term here that for that term and all terms onwards, they are bigger than it. So it does get and stay indefinitely big. And now we have a problem, because we have this domain sequence that converges to some value that we've called p, and we know that p is going to be inside our domain. It's going to be inside the interval ab, and we know that because the domain is a closed interval. It contains its boundary points a and b. So the biggest the terms of this sequence could possibly be would be b. So if the sequence was b, 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 it would converge to b. It can't possibly converge to something that's bigger than b. Equally, the smallest the terms of this sequence can be is a, and if it was the constant sequence a, it would converge to a. It would still converge to something inside the interval. It wouldn't converge to something lower than a. Contrast that to if it was an open interval, then you could have a sequence that was inside the open interval that was converging then to the boundary points a and b, which weren't included in the domain. But because it's a closed domain, we know that if it's converging to p, p must be inside the interval. So this causes a problem because the function must be continuous at p, because the function was continuous everywhere inside the interval ab, and therefore the limit as x approaches p of the function is equal to f of p. But that means that the image sequence of our sequence that's converging to p in the domain here should converge to f of p. So this sequence here, f of x2, f of x5, f of x8, f of x9, etc., it should be converging to f of p, but it's not. It's tending to infinity, and that's where we have a contradiction. So we have contradicted p being continuous, the function being continuous at the point p. So this is nonsense. The function cannot have been unbounded above. Now, as I say, we're not going to do the case to show that it cannot be unbounded below, but the strategy, I hope you can immediately see what it would be. It's exactly equivalent to what we've just done to prove a contradiction if we assume that it's unbounded above. So I hope we now all agree that the function is going to be bounded above and bounded below over its domain. What we can now consider doing is constructing the image set for the function over its domain. So we take all the values f of x, where x is allowed to vary over the whole domain, the interval ab. So basically go to every single point in this domain, ask what is it being mapped onto, and put that value into this set, collect them all together, and that's the image set of the function over its domain. Now this set is going to be bounded above and it's going to be bounded below. That's what we've just shown. So by the completeness axiom of the real line, because it's bounded above there will be a least upper bound, and because it's bounded below there will be a greatest lower bound. The fancy terms are of course supremum and infimum. So the supremum of I is going to exist and the infimum of I is going to exist. We'll call the supremum of I capital M and we'll call the infimum of I little m. And now what we want to prove is that there is going to exist points inside the interval that are mapped onto these two values. So there's going to exist a d that is mapped onto capital M and a c that is mapped onto little m, and then we'll have shown that the function obtains its minimum and maximum values. So the way in which we're going to prove this is actually extremely similar to the way in which we proved the previous part. Again, really, there's two separate cases that I need to prove here. I need to prove that there is a d that is mapped onto big M, and I need to prove that there's a c that is mapped onto little m. I'm going to be lazy again, however. The proof of these two things follows exactly the same strategy. It's pretty much identical. A few little adjustments, but very easy to make adjustments. The overall key ideas, crucial, difficult ideas, are exactly the same. The strategy is the same. So we're only going to do it for one of them. So we'll take big M. Everyone prefers big M to little m. So we'll show that there's a d that is mapped onto big M. But the proof strategy for showing that there's a c that is mapped onto little m is exactly the same. So as I've said, it's got similarities to the proof strategy that we saw previously. So again, we're going to consider creating a special domain sequence with a corresponding image sequence that's going to obey certain properties. So I'm going to pick my first term for this domain sequence, and it will have a corresponding image term here. And I'm going to pick it so that that corresponding image term is inside this half open, half closed interval from m-1 to m. So remember, m is the supremum of the image of the function over the entire interval from a to b. So m is greater than or equal to all the values of the function over this interval ab. Here is m on the number line. We can then consider this number m-1 here. Now, because m is the least upper bound, it means that any number that's smaller than it is not an upper bound for this set. So it means that there must exist some point in the domain such that it is mapped onto something that is bigger than m-1. So that m-1 cannot possibly be an upper bound. So I will be able to find a point, that's going to be the x1, such that f of x1 is inside this interval from m-1 to m. So it's bigger than m-1. It could be m itself, but it's something inside there. So that's how we'll choose our first term. Let's now move on to our second term. So we're going to choose our second term, and it will have a corresponding term in the image sequence, and we're going to choose it such that the corresponding term in the image sequence, f of x2, is going to be inside this interval from m-1 to m. So in the case of the first term, we had m-1 over 1 here. In the case of the second term, we've got m minus 1 over 2. In the case of the third term, it's going to be m minus 1 over 3. In the case of the nth term, it's going to be n minus 1 over n. So looking at what this means on the picture, here is m minus a half, so it's closer to m. Now, again, m minus a half cannot be an upper bound because it would contradict m being the least upper bound. So there must exist some point in the domain that is mapped onto something that is bigger than m minus a half, i.e. something in this interval. Now, there might be multiple points, but there is at least one of them. So we can find, therefore, that point, we can make it the second term in our sequence, and then we'll have this corresponding term in the image sequence. And of course, x1 and x2 aren't necessarily distinct real numbers in our domain. They could have been the same real number. So if this first number here, making the first term, had f of x1 that was very close to m, it could have even been equal to m, for instance, then it would satisfy the condition of being inside this interval, but then it's also going to satisfy the condition of being in this interval, so it could be used as this second term also, and maybe even the third term. If it's actually equal to m, then it could actually be used for all the terms. If it's not equal to m, then at some point we're going to make this small enough, this m minus 1 over n is going to be small enough that it's no longer going to be mapped onto something inside that interval, and then we're going to, at the least, have to move on. So you're going to continue building these sequences in this way. So x3, you'll choose such that f of x3 is inside the interval from m minus 1 over 3 to m. And then you'll continue on x4, x5, x6. The general xnth term is going to be chosen such that f of xn is inside the interval m minus 1 over n to m. And you're always guaranteed to be able to find such an xn because m minus 1 over n cannot be an upper bound, and therefore there must be something that is bigger than it. So clearly this image sequence that we've constructed here is going to converge to big M, because the terms of this sequence are going to get and stay indefinitely close to capital M because of the way that I've chosen them here. If you go, for instance, to this fxn term, that term is inside this interval here, so it's within 1 over n distance of m. All the subsequent terms are then inside that interval as well, because they're actually in even closer intervals. So this next term along, fxm plus 1, that's going to be inside the interval m minus 1 over m plus 1 to m, which is contained inside this interval, and then the one after that is inside an even smaller interval. So this term and all the terms beyond it are going to be inside this interval, i.e. within 1 over n closeness of big M. And then you can go on, making this 1 over n indefinitely small. So it is true that the terms of the sequence will get and stay indefinitely small. However small you want, I can find you a point in this sequence, a term in this sequence, such that that term and all the terms beyond it are within that closeness of capital M. So if I could conclude that this domain sequence converges to some value p inside the domain, and I've put a question mark there because I'm not actually going to be able to conclude this, then we'd be done if I could conclude that, because we know the function is continuous everywhere on the domain, so it's going to be continuous at the point p, meaning that the limit as x approaches p of f of x is going to equal f of p. But if this domain sequence converges to p, then its image sequence must converge to the value of the limit as x approaches p of f of x, which is f of p, but it's converging to m, so we'd then be able to conclude that f of p is equal to m, i.e. here is the magic point. We can use this p as our point D. But of course we can't conclude that this domain sequence necessarily converges to some value p inside the domain. So we're almost thwarted, but of course to the rescue comes the Bolzano-Weierstrass theorem once again. All the terms of this sequence are inside the interval AB, therefore the sequence is bounded, therefore it contains a convergent subsequence. So there's going to exist some subsequence that does converge to some value p in the real line, and of course because all the terms are inside the closed interval, we know that the thing that it's converging to must be inside the closed interval also, so p is going to be somewhere inside our domain. So this example subsequence here, I apologise for how wonkily it's written, is representing our subsequence that converges within our domain and it's converging to value p. it will of course have a corresponding image sequence that I've written out here, which is going to be a subsequence of the original image sequence, which we know converges to M. We know any subsequence converges to the same thing as the overall sequence, so this image sequence is going to converge to capital M. So bingo, now we're done. Here we have a domain sequence that is converging to a value p in the domain. We know, because the function is continuous over the entire domain, that it's going to be continuous at p, so we know that the limit as x approaches p of the function is equal to f of p. So when we look at its image sequence here, its image sequence must converge to the value of this limit, i.e. it must converge to f of p, but we know it's converging to m, and therefore we can conclude that f at this value p is equal to this m, so p will be our magic d. So we've found a point in the domain that is mapped onto this capital M, which was the supremum of this image set. So everywhere else in the domain, the value of the function must be less than or equal to this value. That's the definition of being an upper bound, and the supremum is an upper bound. So we have therefore shown that the function does obtain its maximum value. As I say, we need separately to prove that it obtains this minimum value, little m, but the proof strategy is exactly the same, with a few very simple alterations that take account of the fact that we're now dealing with the minimum rather than the maximum, so we're not going to go through it. Instead, I'll just briefly outline it for you. So again, you'll construct these sequences. So you'll construct this domain sequence such that the image sequence converges this time to little m. And the reason you can do that is because little m is the infimum of this image set. So it means that there are points in the domain that are mapped onto values that are indefinitely close to little m. Just like for the supremum, there were points in the domain that were mapped onto values indefinitely close to capital M. Then what you'll do is you'll say, take a subsequence of this domain sequence that converges to a value p. You'll then have its corresponding image sequence, which is a subsequence of the image sequence up here, and you'll know this converges to little m. And then you again apply continuity to say, therefore, that this value that the image sequence is converging to must equal the value of the limit of the function as x approaches that point, and therefore f at that point must equal little m. So congratulations to us, we've done it. We've proven that if you have a function on a closed interval ab that's real valued and is continuous on the entire domain, then it must be bounded above and bounded below, and it must obtain its maximum and obtain its minimum, i.e. obtain its extreme values. So thank you for watching, we'll finish there.